Hey, hi everyone. Welcome to the first live member seminar series of the quarter. Today we are very happy to have Sebastian Mizera from Columbia University, who's going to tell us about unitary architecture of renormalization. Please take it away, Sebastian.
All right. Well, Happy New Year, everyone. And thank you so much for the invitation to give this seminar. And thank you for coming as well. I hope to be able to visit Chicago at some point in the future in person as well. So today I will be talking about two papers that appeared on the archive just a few months ago. And both of them are written together with my fantastic collaborators, Ameya Chavda, Dan McLaughlin, and John Stanton. And all three of them are graduate students at Columbia. Okay, so as you might have guessed from the title of this talk will be about renormalization. So renormalization is a famously confusing subject, but don't worry. The goal of this talk is to be able to present a perspective on renormalization, which is kind of from a different point of view. Okay, so don't worry. For now, the first thing that I'm going to do is going to kind of introduce some of the basic notions behind the RG, and later on I will tell you about some new on-shell approach that exploits unitarity. Okay, so let's start slowly. Renormalization basically means that is the notion of the fact that the physics changes depending on the scale at which we probe it. And I think there's no better way to illustrate it than the theory of strong interactions, so quantum chromodynamics or QCD. In this case, what you can do is you can measure the strong coupling as a function of the energy at which you probe it. Okay, so this plot here is going to be a collection of many experiments that over the years have measured alpha s, so the strong coupling, as a function of the energy Q here. And what you can see is certainly the fact that the coupling changes. So we say that it runs with the energy. And one example change is that at higher and higher energies, the coupling becomes weaker and weaker, which is a famous fact of the asymptotic freedom. Okay, so renormalization is important. We measure it, so we want to understand it better. And what I'm going to do today is try to understand it from the theoretical point of view. Okay, so before kind of jumping in, let me remind you about a couple of standard ways that we talk about renormalization. So you might have encountered these kind of diagrams in your courses on quantum field theory. These diagrams are so important, they made it to the cover of Peskin and Schroeder in here. So the typical way that we learn about RG is through the so-called renormalized perturbation theory. That is the perturbation theory in which we insert counterterms into the Lagrangian and then compute the renormalized quantities by including those counterterms. Okay, so there's a couple of buzzwords that you might have encountered when you studied renormalization. For example, there's the important concept of the BPHZ forest formula, which tells you how to renormalize divergences that are either overlapping, nested, or overlapping and nested, and how the consistency of the combinatorics of different diagrams is giving you consistency of the renormalization. Okay, so that was an important part of the proof. You might also have heard about the BRST formalism in the context of gauge theories, or even more technical terms like the R-star operation, which nowadays allow us to perform the RG, or compute the RG properties of the RG to high precision. Okay, so these are the standard buzzwords. Actually, for the purpose of this talk, you don't need to know any of them. The idea is to revisit the RG from a different perspective. So the bottom line here is that everything here works, but you have to do a lot of, you have to grind for the computation. Okay, so you need to have a lot of computing power or a lot of graduate students alternatively to perform those computations. Okay, so in this talk, I will be talking about a different perspective. I wanted to think of it as an idea of the on-shell perspective on renormalization, but actually I decided to call it a dream because it's kind of has always been more distant than many other ideas. And here the on-shell perspective refers to this notion of well, you can also call it the on-shell philosophy that dates back to the ideas of Heisenberg, which says that the physics should be explained entirely using observable or on-shell quantities. Okay, so nowadays we refer to it as the S-matrix program or scattering amplitudes, what have you. And some of the properties that we would expect from this philosophy is that we want to avoid talking about gauge redundancies or gauge symmetries, which tend to drop out at the end of the computation, but are there in the intermediate stages. Likewise, we want to avoid talking about Feynman diagrams for kind of similar reasons of kind of large redundancy in the computation. And some people push it even to the extreme of not wanting to talk about Lagrangians at all, just the observables. Okay, so the first question that we should be asking ourselves here is why? Why is it in general a good approach? And there's a couple of standard answers to this. The first one is that if we avoid gauge redundancies, well, as I mentioned before, if you can avoid having the baggage of additional terms in the intermediate stages of the computation, then, well, the computations become easier. And that's exemplified by many applications. That's one of them I will review in a second. Okay, so that's a very practical answer to the question of why. A more kind of theoretical answer is that, well, we might be uncovering new structures and new symmetries that might be easier to see when you don't have redundancies in your computation. And lastly, let me also mention the kind of one aspect that should not be underappreciated, which is that of pedagogy. If we can explain things in a simpler way, then it means that we can shape the way that people think about, or the next generation of physicists thinks about a given concept, which I think is always useful. Okay, so let me give you one example in which just in the field of the S-matrix or scattering amplitudes, in which that has been, well, it's a success story, really. And the example is that of computing the cross-section for, say, two gluons with positive helicity going into a number of other gluons, let's say also with positive helicity for simplicity. In the standard approach, if you did this computation using Feynman diagrams, well, each diagram individually would be gauge dependent. So there will be a lot of redundancies that are going to cancel out at the very end once you add them up. And actually, if you try to compute the number of diagrams, or the number of terms rather, that appear in this direct computation, the number would be a billion with a b, 10 to the 9. Okay. However, by now, we know very well that the final answer simplifies rather drastically. So this is the result due to Park and Taylor from a long time ago, is that the total cross-section is actually proportional to this single term. So out of 10 to the 9 terms, only one survives, or rather they conspire to kind of cancel out, and everything just depends on the dot products of the momenta of the external particles in this combination. Okay. And later on, this kind of led to a revolution in the computations of scattering amplitudes, particularly in gauge and gravity theories, and eventually to the formulation of the recursion relations that deal only with on-shell quantities directly instead of Feynman diagrams, which are off-shell. Okay, so this was kind of the setting up the stage, and let me kind of draw a couple of parallels here in the theory of RG. So for the purposes of this talk, I will be focusing on the massless 5 to the 4 theory with a single coupling lambda in 4 dimensions, okay, which is kind of usually the benchmark of how well we understand RG, and I think it's a good benchmark for new techniques as well. Okay, so here, as I said before, you can just insert counterterms, all the standard buzzwords, you can grind through the computation and you would get the final answer. And the final answer could look something like this. Okay, so this is the beta function for the coupling lambda, which depends on some scale mu. The beta function is simply the derivative with respect to that coupling. And we know that it's been known for a long time that the leading terms look something like this. Okay, so the beta function is the lambda squared, lambda cubed, and so on terms. And up to these normalization factors of pi and so on, they're just rational numbers, right? So we have some 17 over 768. And to me, this kind of calls for a better explanation. So ultimately, if we're just computing a simple fraction, then there must be a better way to understand it, kind of in a similar way to there must have been a better way to understand the Park-Taylor cross-section. So in this talk, I will attempt to give you an alternative description for how to obtain these quantities that do not have anything to do with Feynman diagrams or with counterterms or anything like that. Okay, so at this stage, let me kind of emphasize that in this theory, as I said, it's kind of a benchmark. In this theory 524, we actually know the beta function to 7 loops due to the work of many, many people listed here. So today I will not go all the way to 7 loops. I will be only for kind of pedagogical purposes, I will be focusing on the 1 loop and 2 loop beta functions. And hopefully these kind of techniques that I'm presenting today will be able to extend them to higher orders in perturbation theory. And the dream is that we'll be able to match the kind of other approaches as well.
Sorry, I have a question here. Can you go back? Sorry, the beta function is scheme dependent beyond 1 loop. So I find it a little bit strange to put so much emphasis on the final answer of the beta function. It doesn't seem to contain that much particular kind of invariant physical information outside of any given scheme. So can you say what you're really talking about more specifically?
Yeah, absolutely. So actually, it turns out that the beta function in 5 to the 4 theory is scheme independent up to 2 loops. So up to the orders that I showed here.
Certainly not to 7 loops.
Sorry?
Certainly not to 7 loops.
Not to 7 loops. So the scheme dependence starts entering that deferred loop. We'll be actually able to see how that information exactly enters in. And actually, that was actually one of the points that used to be confusing to me, like how do we know it's scheme dependent up to 1 or 2 loops? It was always some kind of a magic computation, but today I will at least explain how the scheme enters in and how do we know a given quantity is scheme dependent or independent. Okay, any other question? Okay, so the goal of this talk is as follows. So I decided to split it into 3 parts. In the first part, I will just give you kind of the intuition why, in a certain sense, you can think of renormalization and unitarity as being closely related to each other. So I'll illustrate it on a time model. And then later on, this time model will kind of guide our intuition to studying unitarity constraints in the full-blown 5 to the 4 theory. And then I will show you that the unitarity constraints in this case actually have exactly the same information as renormalization. And then in the last part of the talk, I will come back to renormalization itself, and I will tell you how we can read off the beta function kind of as a consequence of all these facts. So I'm going to start with the relation between RG and unitarity. So let's start with the following toy model. So let's say we were computing a quantity. Later on, I really want to think of these quantities as the S matrix elements, but it could be anything else computed at 1 loop. So what we have here is going to be the coupling squared in this case, that can depend on the scale mu. And then the final answer is going to kind of take this general form. There's going to be a logarithm and the rest. Okay, the logarithm is something that usually is called a large log, and it really comes from the fact that we have a UV divergence in our theory. So you can think of this mu as a cutoff or some scale with respect to which we measure things. If you've not seen this before, then the existence of the log is actually quite simple. So if you think of these as 5 to 4 vertices in here, and we have a loop with a loop momentum L, and the overall momentum being injected is P. Then at large L, we have two propagators, so 4 powers of L downstairs and 4 powers in 4 dimensions upstairs, which makes this quantity log divergent. And this is the origin of this log in here. Okay. Let me also put in everything that is non-divergent. Let me just call it a constant B. Okay, so this is in a sense an ansatz. A general answer is going to have depend on these two functions A and B. Okay, so let's review kind of the standard way that we could be talking about the RG. Okay, so we have our quantity we computed in perturbation theory. The first term is the tree approximation, then there's one loop and so on. So the tree is just going to be, let's say, the coupling itself. The one loop is going to be the formula copied from the previous page, except for the fact that the cutoff was entirely arbitrary. So let me just choose a cutoff. I'm just going to call it mu star. But because the cutoff is arbitrary, I might as well just write the same formula up to small corrections as this same formula, but with changed cutoff. Okay, so this equation here is the independence of the choice of mu. In this line, there's mu star. In this case, there's some mu, other mu. And now the question is, how can I make these two expressions equal? And the answer to that question is that these two expressions are only equal if we allow the coupling to run. Okay, so that's how we know that the coupling has to change with the scale at which we measure it, or alter in the different interpretation would be the scale of the cutoff. We know that G mu, if you plug it here, has to be equal to the reference G mu star, so the kind of the subtraction point, the reference point, plus a correction that has this logarithmic dependence that translates between the second line and the first line in here. So if we wanted to talk about something like the beta function, so this log derivative of the coupling, well, from that perspective, we're doing the derivative with respect to mu. So the first term here is a constant. This term here has a mu dependence only in the denominator. So if you compute this derivative, it's proportional to this A. So in fact, everything to leading order that we want to know about running is contained in this constant A. So the lesson from this is that the coefficient of the log, so A was the coefficient of the logarithm, actually governs the running. Okay, which is how we usually think about the RG. Okay, now let me switch gears slightly and let me talk about unitarity. So as I mentioned before, I wanted to think of it as the kind of S matrix statement. So unitarity at the level of the S matrix operator tells us that SS dagger is equal to 1, which is the statement that all probabilities add up to 1. So here S is the scattering operator, which very often by convention is decomposed into the fully non-interacting piece, and T, which is the interacting piece. Okay, so if you plug in the second line into the first line, then we get a quadratic constraint on the T, on the interacting piece of the S matrix, which reads as follows. So we get this equation, which you might recognize in a simpler way as the generalized optical theorem. So what we're looking at here is that the left-hand side, we're going to both sides we're going to sandwich between an in and out state. So we're going to have matrix elements. On the left-hand side, we have a matrix element of in going to out, say represented with some picture like this. On the right-hand side, we're going to have the in going into some intermediate state. So we're going to insert a resolution of identity between T and T dagger, which is going to be a sum over all intermediate onshore states and an integral over their phase space. Okay, so this sum here is the sum of all states and integral over their phase space. And then we have T dagger on the right. Okay, so that's known as the optical theorem or the generalized optical theorem. Okay, so let's actually apply this this generalized optical theorem to the example of our time model M. Okay, so on the left-hand side, if we have one loop, it's going to be something proportional to the coupling squared. On the right-hand side, the only option that we can actually split it into two pieces is as having tree-level squared. And then we have the integral here over the phase space of the intermediate two particles. Okay, so then on the left-hand side, I'm just going to plug in the ansatz that we've seen before, the one with the log, with the A and the B. On the right-hand side, I'm likewise going to plug in the same quantity that we've seen on the previous slides. It's just the coupling itself. Okay, so what comes out is here, on the left-hand side, we're going to have, let's say we commit to a time-like momentum, which in my signature is going to be p squared positive. This means that the only imagined part of, well, here I'm assuming that A and B are real, which I'm going to gloss over the detail. Then the only source of the imagined part is going to be the logarithm here that gives me some factors of pi. And likewise, on the right-hand side, this integral here is easy to evaluate. It's the integral over the phase space. So I get the integrand is equal to 1. So I get the volume of the phase space, which likewise is some factors of pi. So after canceling out the couplings, g squared, what I have is that I have a constraint on A. And in this case, A was the same A as before, right? It's the one that we used to constrain by running. Now we constrain it by unitarity. So the lesson from this exercise, hopefully it gives you some intuition that the running has something to do with unitarity. And it's all basically a consequence of this simple observation here that if we compute the log derivative of a logarithm, then it tells us about the scale dependence, at least of marginal couplings. And then on the right-hand side, if we compute the imagined part, well, they're equal up to some proportionality constants, and the imagined part is the one that is governing unitarity. Okay, so really the observation is that it's going to be all about extracting the coefficients of the logarithms that are going to be accessible through unitarity, but at the same time, they're going to tell us about running. So I have to say, so you should really think of these two concepts as being interchangeable, at least to some extent, that I'm going to cover in the rest of the talk. And I should say that this observation has been made over the last couple of years, especially in this paper of Koshinsky et al. And Karnwald and Wilhelm, who have used it in various contexts. The goal of this talk specifically will be to uplift this simple observation into a full-blown theory of renormalization. So basically, what you're going to see over the next half an hour or so is going to be a more fancy version of this trick. In fact, what I'm going to formulate is what we call the Unitarity Flow Conjecture. It's going to be, let me kind of give you the hand-wavy definition at first, and then we're going to make it precise throughout the talk. The conjecture is that imposing unitarity on the S-matrix elements is going to give us exactly the same information as renormalization without any concepts that have to do with running or counterterms or anything like that. And we're going to see there's actually a weak and a strong version of the conjecture, but for now, just think of this as a concept, and then I'm going to make it precise. Okay, so I'm going to move on now to the second part, in which I'm going to tell you more about the unitarity constraints, unless we have any questions in the meantime.
Actually, are you thinking about the cutoff as real or complex?
I'm thinking of the cutoff as being real. Yeah. All right. So let me move on to the unitarity constraints. At first, I'm going to focus on the four-particle amplitude. The reason why we're focusing on the four-particle amplitude is that we have quartic coupling that we want to probe in 4 dimensions. So the amplitude is going to depend on the momenta P1, P2, P3, and P4. Actually, it's not going to depend on the momenta directly. It's going to depend on the momenta for these kinematic or Mandelstam invariants S, T, and U. And let me give you the kind of general parameterization of the amplitude that we're going to use. It looks something like this. So let me explain it step by step. So first of all, it's going to have a lot of logarithms of the cutoff mu squared minus some quantity x, where x can be either S, T, or U. Okay, so because these logarithms are going to appear a lot, let me just introduce a notation for it, like the one in here. Okay, the 3 lines here have the ansatz for the tree level, the 1 loop, the 2 loops, and so on and so on. Okay, so let's look, for example, at the 1 loop answer. The 1 loop answer looks exactly like the toy model that we've seen before. So it has some coefficient in here. I'm going to call this coefficient M11. So it's a coefficient of the 1 loop with a single logarithm, the 1 logarithm. And it's you can of course write a more general ansatz, but in this talk we'll be assuming permutation symmetry. So everything is STU symmetric. So because of that, all of these logarithms have the same coefficient. Okay, so just like before, we have the coefficient of the log, and we also have the constants. And this kind of continues at higher loops. So for example, at 2 loops, we have M22, which is the coefficient of the double logarithms. There's the M21, which is the coefficient of single logarithms, and M20, which is the coefficient of the constant.
Is it possible to get something like LS times LT plus permutations?
Yes, so indeed, it's possible. In principle, it would be possible. It's not forbidden by symmetries. I'm going to actually come back to it in the slide for the experts to have cross terms. We actually included them in the paper, but for the purposes of this talk, I'm going to skip them because they will be 0. Okay, so the first observation here is that these constants in here are actually a scheme. Okay, and the reason for that is that I can just set what is the value of my amplitude at a given scale. And at that scale, I can just read off these constants. This is actually a very convenient scheme that is very often used in computations, or at least in the discussions on the RG, which is the on-shell scheme. So what I could have done is I could have set all these constants to be 0. Okay, all of them except for the tree level, of course. And the property of this choice would be that the amplitude evaluated at the kinematic point in which S, T, and U are equal to minus mu squared. In those cases, it would be a log of 1, which is 0. So all of these logs would drop out, and the value of the amplitude in the scheme would be simply the coupling. Okay, so that's known as the on-shell scheme. Okay, so let me actually organize all of this data into the following table, just to make it slightly simpler to read. So basically, all the information about the amplitude can be actually summarized in these constants in here. So we have things at tree level, at 1 loop, 2 loops, 3 loops, and so on. So all of them, I'm not actually going to explain it fully, but you can argue all of these are real numbers, and really these are the things that you would need to compute. If you can compute all these numbers, it's the same statement as saying that you know what the amplitude is at all energies. Okay, so what do I have here? Well, first of all, there's some little convention to make it uniform with the rest of the table. I actually call this coefficient here, which would be M00, so tree level, constant term. I call it 1/3 because of this symmetrization here. So we have 1/3 times 3 because of the STU symmetry. That's just notation. And let me emphasize, well, maybe before that, I can explain the columns as well. So the first column here is the coefficient of the leading logarithms. So at L loops, we can have up to log to the Lth power. So these are the coefficients of the leading logarithms. These ones in here are the subleading logarithms, there's sub-subleading, and so on and so on. Okay, so let me give you an example. If you actually wanted to compute one of those constants, okay, so let's say this data point in here, then what you would have to do is you would have to enumerate all Feynman diagrams. You would have to compute all these diagrams in whatever way you want, then expand it such that you're sensitive only to the leading logarithm, and the coefficient of that, so coefficient of the log to the third power, summed over all diagrams, would be called M33. Okay. As I will explain in a second, that approach, kind of direct computation, would be hugely wasteful. And in fact, the M33 is determined fully in terms of lower loop answers. Oops.
Sebastian, maybe I'm confused or not up to date, but are you saying that it's not possible to have more complicated functions ever appear in scattering amplitudes than just powers of logs?
Yeah, so what I'm doing here is I'm expanding the, sorry, I didn't maybe fully explain this. I'm expanding everything in the high energy. And the reason for that is that we're probing the UV. So in that expansion, this is the most general ansatz that you can have. So you might be familiar with things like multiple logarithms, elliptic functions, and so on and so on. All of those, if you expand them in high energy, have to be of this form. Have to be logs by power counting, so there's no dimensions. So for example, a dilogarithm would expand to a log square at high energy.
Why is log the only dimensionless function? I'm sort of confused. You have mu and you have s, t and u. Why can't you make more complicated functions?
Yeah, so I'm only collecting the power for the purposes of this approach. It's only important to collect the powers of mu squared over kinematic invariance. There could be things like log of s over t, if that's what you have in mind. This would we would shuffle into the constant. It's a constant.
Why only log? What's the principle that tells you only log or powers of log?
I see. Yeah, there's some math theory behind the types of functions that can appear in computations, and these perturbative computations of Feynman diagrams. They're so-called holonomic, and the general result is that if you expand it in limits, then they can only have polynomial powers and the log powers of log. In this case, we cannot have polynomials because of the mass dimensions, so we have to have logs.
The buzzword there you said was holonomic? Okay, thank you.
Yep.
Can I ask why you can't have cross terms between the different logs?
Yeah, so there was a question about that just a second ago, and I said in principle you can, but we proved that all the coefficients of that, at least in the order that we're going to work at, are 0. So I'm going to actually circle back to that in a few slides. Okay, so we have this table, and let me also emphasize that in principle, all the terms in this strip are actually a choice of a scheme or equivalent to the choice of the scheme, even though we usually don't talk about it in this way. Okay, so now
to clarify that assertion, you're saying those are the only terms in this expansion that are scheme dependent? Everything else is scheme independent?
No. No, so these are the at every loop order, there's one degree of freedom that we can fix by a scheme, and this you can think of them as the source of that scheme. What I will be actually arguing throughout this talk is that all the other terms in this table are actually functions of these ones. So they will be also dependent on the scheme, but they're not like a new degree of freedom. Okay, so let's now come back to unitarity. So unitarity, we can treat it as this optical theorem. So first of all, what we have to do, we're going to apply it to a 4-point function. On the right-hand side, this looks quite complicated because we have to sum over all intermediate states. Because I will be focusing on a Z2 symmetric theory, so 5 to the 4, this actually simplifies somewhat, and instead of having to sum over all possible states, I only have to sum over only the even number of states. Okay, so we have 2 particles going across the cut, 4 particles going across the cut, and so on and so on. Okay, so let me also emphasize these are not Feynman diagrams, these are full on-shell quantities. So for example, here on the left-hand side, we have the M4, the 4-particle matrix element, the thing that we're interested in. On the right-hand side here, we have the cut between the M4 and its complex conjugate. And then this continues, and we have 6-particle amplitude and its complex conjugate, and so on and so on. So one perhaps surprising thing is that if you ask the question of full-blown unitarity, you have to take into account the whole equation. But if you're only interested in the leading logarithms, so the highest powers of the log, a little analysis tells you that actually only those terms matter, only the 2-particle cuts. And then the similar analysis for the subleading logarithms would tell you that only the 2-particle and the 4-particle cuts matter. Okay, so what I'm going to do is I'm going to first focus on the leading ones, and then I'm going to kind of give you the story for the subleading ones, which is very similar. Okay, so the leading logarithmic order, if we take the formula from here, we obtain the following unitarity constraint. So let me see. So here I've introduced a new notation in which the subscript L is going to denote the Lth loop order. So here we have the 4-particle amplitude at L loops. So that by unitarity cut, if you expand both sides, can be obtained by gluing together L prime loops and L minus L prime minus 1 loops, so that they sum to L minus 1, with the additional loop being the one that you cut through. Okay, so basically this is the consequence of the optical theorem. And now it's quite simple, because now we simply take the ansatz that I've shown you a few slides ago, and then we plug it into the imaginary part on the left-hand side, and likewise the right-hand side. Okay, so then you do the computation, and you get a constraint not on the full amplitude, but on these coefficients that we're interested in constraining. Okay, in fact, you get the following recursion relation in which the leading logarithm at L loops is constrained as a quadratic combination of leading logarithms at lower loops, with the boundary condition for this being that at tree level we get a third. Okay, this can be actually quite easily solved, and it tells you that the LL component is simply a power of 3/2 raised to the Lth power. Okay, so just like that, with unitarity, we actually managed to constrain this whole tower in here of leading logarithms. And recall that, for example, this one would normally be obtained as a consequence of computing, Feynman diagrams. What I've just told you is that this information is very redundant because everything is in fact fixed by tree level and unitarity. So tree level and unitarity fixes this whole column, and you never have to actually compute anything at this order. Okay, so now you might kind of guess where this is going. So let me spell out some of the details for the subleading logarithms, which are in this column. Okay, so at the subleading logs, you have the unitarity constraint, which once again, you can expand it in terms of cuts on the right-hand side. In this case, we have the cuts for the 2-particle cuts, and then the new term is the 4-particle cuts. So the 4 particle cuts involve a 6 particle amplitude, 1, 2, 3, 4, 5, 6. So that means that you actually have to have some information about the 6-point amplitude. But here is where the fun begins, because the 6 particle amplitude itself satisfies a very similar identity implied by unitarity. In fact, you can show that only the following terms matter. So the major part of the 6 particle amplitude, once again, can be cut. Because of the Z2 symmetry, only the following terms matter at this order. So what you can do is first actually solve this unitarity equation for the 6 particle amplitude, take the answer for that, and plug it back into this unitarity equation in here. Okay, so details of that are in the paper. I'm not going to bore you with all the nitty-gritty. The result of that, however, fits in one line. So this is the recursion relation for the subleading logarithms. Okay, so in this case, once again, we have a sum over lower loop answers. And in this case, we have 2 boundary conditions. One is the one that we've had before, and the other one is going to be M10. M10 is in fact the choice of a scheme. Okay, so M10 is not determined in this case. Okay, with a little bit more work, you can actually solve this recursion relation. So the solution looks like this. It's slightly more complicated. It involves these harmonic numbers in here, and also it's scheme dependent. Okay, so as promised, all the kind of lower things in the table inherit the scheme dependence from the one loop constant term.
Sebastian, can you go back to the here the reason why you need only the imaginary part of the 6-point amplitude, even though the unitary constraint involves the entire M6, is just because that's the only part where the logarithmic comes in?
Yeah, exactly. Yeah. So here's the summary in case, just to summarize everything. So the second column in here had the subleading logs, the coefficients of the subleading logs. All of them are fixed by the recursion that I've shown you before. And the source for this recursion is the scheme at one loop, and also the information from the leading logs in here. So you might guess where this is going. In fact, that's a part of the conjecture. The conjecture would be that at every loop, at every logarithmic order, you can actually fix everything in terms of the initial conditions, which would be the scheme that we talk about, which are these coefficients here, in which the second slot is 0, meaning these are the constant terms. And we conjecture that all of the other powers can be fixed in a very similar way. Okay, so now that we have this we have these constraints, what we can attempt to do is resummation. So we can take only the leading logs and you can resum them, or only the subleading logs and resum them. It's well known how to do that. So this is the answer. So for example, the first line here comes from resummation of the leading logs, in which we have this logarithm of S and similar terms for T and U. And likewise, the subleading logarithms are going to give you this kind of resummation in which we have a log of a log. We also have this scheme in here. This is for the S channel, and there's similar for T and the U. Okay, so this term in here is the famous Landau pole, okay, where perturbation theory breaks down. The predictions break down at some exponentially high energy. And notice that this is actually a finite. This is the example in which the individual divergences at every loop order actually cancel out. So the answer for that is entirely finite. Of course, this is at this stage, we've not done renormalization or anything like that. We've only used unitarity, but we've seen that even though we only use unitarity, we've recovered a result that normally would be a consequence of renormalization. So that's kind of instantiating the relationship between the RG and unitarity that I was hinting at the beginning. Yeah, so before moving on, let me actually address this question that we've had already 2 times in the questions about the mixed logarithms. So in principle, we could have had terms of the form log of s times log of t times log of u raised to some powers, some non-zero powers. And indeed, you can actually include those in the ansatz. This is what you should actually start from. I skipped it for the purpose of this talk, but if you're interested in the details, you can either ask me later on or have a look at the reference in which we actually explain why the coefficients of all these mixed terms are equal to 0. This is actually related to something that the experts called the Feynman relations. Okay, I guess for completeness, let me mention that the entirely analogous story you can repeat for the 2-particle amplitude. Once again, you can write the ansatz. The amplitude depends only on the momentum p. So we have a log of p, log squared at 2 loops, and so on and so on. Okay, so there's some ansatz where the n's in here are the new coefficients that you want to constrain. And the logs are as before. So we have the 1 loop, we have the 2 loop, we have the scheme dependence, which are the constant terms. Everything is the same. Now the unitarity, in fact, becomes this equation to the leading order, in which the major part of the propagator is the cut over the free particle phase space. So we always have to have an even number of particles. But now the major part of the 2-particle amplitude is constrained in terms of 4-particle, which is something that we've already done. Okay, so then you can repeat the whole procedure, and you can actually write the recursion relations, you can solve them, and the answer that you would find is that to leading order, we get a 0, so the leading logs are 0, and the subleading ones look somewhat like the leading ones for the 4-particle amplitude. Okay, so if you wanted to repeat the same constraints on the M2, then you would find that you can fix the leading coefficients and subleading coefficients, and then conjecturally also all the other ones. Okay, so moving on to the last part of the talk, let me kind of wrap it up and tell you how this is related to the usual way that we think about the RG, and finally talk about things like the beta functions. Okay, so we recovered all the basic tenets of the RG from unitarity alone. Let us talk about the connection to the conventional discussion of the RG. Okay, so the one starting point would be to maybe start with the renormalization group equation, or the Kalan-Semanzik equation, which looks something like this. So on the left-hand side, we compute the total derivative of the renormalized amplitude. So this is the same object as before. And then we would claim that everything is cutoff independent, at least up to leading orders, which is the statement that this has to be 0. And then on the other hand, what we can do is we can expand the total derivative in terms of the partial derivative, the derivative using the chain rule, the derivative with respect to the coupling, which is telling us about the renormalization of the coupling, and the anomalous dimension, which is the running of the 1-particle wave function. Okay, so the most general Taylor expansion that you can make is going to be that the beta function, if you didn't know anything about the RG, in principle, it would be something that has a constant, a linear term, quadratic, cubic, and so on. And here I've sprinkled in the conventional factors of 16 pi squared. And likewise for the anomalous dimension. Likewise, it would have the constant, linear, quadratic, and so on. If you just plug in the ansatz into this equation, you would find immediately that actually for the beta function, the linear and the constant terms have to be 0, likewise for the gamma. So actually, the things only start at the one loop order for the beta function, which is why I called it beta 1. And this one I called beta 2, likewise gamma 1 and gamma 2. Okay, so now with the setup that I presented, what you can do is you can simply take the ansatz that I've shown you before, and plug them into this constraint, and then you can derive recursions. So just like before, you can derive constraints for the leading, subleading, and so on constraints. So let me actually illustrate in a table the comparison between the RG and the unitarity constraints from this perspective. Okay, so if you plug in the ansatz into the RG formula, the Kalan-Semanzik formula, you would obtain the following recursion relation. It looks very much like the one that we obtained from unitarity, or somewhat like it, in that it depends on the lower loop. The major difference is that we have an explicit L dependence in here, L being the loop number, which means that the solution is going to be more complicated. It also depends on what I call beta 1 and gamma 1, which normally would be called to the one loop beta function and the one loop anomalous dimension. So actually, another major difference is in the initial conditions. First of all, you need the initial conditions for the recursion, which could be the tree level, the M00, but you also have to know these constants from this point of view, which are the beta 1 and gamma 1. This is to be contrasted with unitarity, which only has one initial condition. And that's actually, so you can treat beta 1 and gamma 1 as the extra input, and that's actually very good for us, because it means that what we can do is we can simply run the unitarity constraints, and then later on require that the recursions we get from the RG and unitarity match, and from this match we'll be able to read off the beta 1 and gamma 1, which is some one way to describe the RG in the conventional way. Okay, so the solution to this recursion looks like this. It's slightly more complicated than what we've seen before. And the reason for that is that there's this L dependence in here, which actually gives us these gamma functions in the solution. And this is to be contrasted with the unitarity solution, which not only does not depend on beta 1 and gamma 1, it also is much simpler. Okay, so now what we can do is we can simply demand that these two functions are equal to all loop orders. And what we will find is that the beta 1 is equal to 3, which is the integer we were looking for before, and gamma 1 is equal to 0. Okay, so here's the summary table. The RG constraints, in fact, did fix all these constants in here. But they required two inputs, the tree level information and the beta and gamma function information. Okay, so similar recursions to the unitarity, but different initial conditions. Now let me move on to the second column, just kind of following the pattern that we've seen before. Once again, we have the RG constraint. The RG constraint now looks like this. So it depends on the lower loop subleading and leading coefficients. And this is to be compared with the unitarity constraint that look like this. Now, the initial conditions for the RG side are as before, meaning M00 and the M10. But now, in addition to that, we have the beta 1, beta 2, gamma 1, and gamma 2, which in the usual parlance would be called the 1 and 2 loop beta and gamma functions. Okay, this is to be contrasted with the unitarity initial conditions with respect to which we have the extra input, these ones. Once again, this is good for us because we can now translate the unitarity constraints into the usual language. Okay, so here's the solution of the left-hand side. Here you actually have to work quite a bit to get this solution. And it involves these digamma functions, the gamma functions in here. And it has dependence on beta 1, beta 2, gamma 1, and gamma 2. Okay, this is in contrast with this side, which was much simpler, and it certainly fitted in one line. But once again, we can use this to match, and the match is as follows. We have that beta 2 is the 17/3, and the gamma 2 is 1/12. Okay, so as promised, now these fractions are just a consequence of unitarity. There's actually one observation that we can make here, which is I didn't know about it before starting this project. Well, I knew that the one-loop beta function is scheme independent. I didn't know that the two-loop beta function in this theory is also scheme independent. How does it arise in this construction? Well, the way it arises is that both recursions have the dependence on the scheme M10, M10. But after you do the match, the dependence on these constants actually drops out, and the result is fully scheme independent. Okay, and as far as I know, this is a known result, but it was shown in a very painful way before, because people usually compute those things only in the MS bar scheme. Okay, so here's the summary slide. We've seen that the first column, the leading logs, are fixed by the org. We've seen that the second column, subleading logs, is also fixed by the org. And I'm not sure entirely if it's a conjecture or a theorem, but I think it's fully expected that all the other towers of logs are fixed by the org as well. Conjecturally, these beta and gammas can be also fixed by matching with unitarity. Okay, so this is the one way in which we would compute them in a fully kind of on-shell way. And in fact, let me come back to this conjecture that previously I kind of vaguely stated as the fact that unitarity constraints give you renormalization constraints. We actually can distinguish, or we wanted to distinguish between the strong version and the weak version. In the strong version, all the beta functions and all the anomalous dimensions are fixed by unitarity. So the claim is that you would derive, unitarity would imply some set of recursions, and those recursions are exactly the same, have exactly the same content as the org. And we actually believe that, at least in the massless Phi-4 theory in 4 dimensions, this is going to be true. So what I've shown you over the last 55 minutes is the proof through subleading order. We conjecture it to all orders. We can also talk about the weak version of the UFC, in which not all, but a subset of beta and gamma functions are going to be fixed by unitarity.
In what sense is the weak one a conjecture as opposed to a theorem?
So as all great conjectures in physics, I'm going to stay kind of at the vague level in here. One situation that you could have imagined is that unitarity has more information than RG. Like there's some parts of the RG that are independent of unitarity. The claim is that it's injective. We can actually make it slightly more precise. What do we mean by that? So for example, in the massive Phi-4 theory, we think that it will remain true that the wave function, the coupling RG is going to be fixed, but the mass renormalization is not. Okay, so that there will be a whole subset that is fixed.
Sorry, Sebastian. To make it clear, so your strong version of the conjecture in the previous example implies that higher betas are going to be fixed in terms of this ML,0, or are they all independent of ML,0?
That the first one, that all of them are fixed in terms of this strip.
Okay, thank you.
Which is the choice of this scheme.
Right.
Kind of unavoidable. Once again, in the on-shell scheme, all of these constants would be 0. Okay, so so let me wrap up the talk since I'm running out of time. So in this slide, let me just mention what's on our minds with respect to the kind of follow-up things that we're working on. So this is kind of the obvious question to keep extending it to higher and higher loops. Not entirely exciting, but if you wanted to do it, then what you would have to include is more and more cuts. So for example, the next term would have 6 particle unitarity cuts, which involve 8 particle amplitudes. We think the conjecture is, I think, is going to go fine there. Another interesting direction is the mass RG. So one interesting aspect here is that once you include the mass, you can actually have a new ratio of scales in which you have the RG scale and the m squared being the mass. So one aspect of it is based on examples is that this, because of the plus sign in here, it actually does not lead to new imaginary parts. So that means that the mass renormalization cannot be directly constrained, but perhaps it can be constrained indirectly if you're sensitive to the real part of the log, not the imaginary part. Another thing that we're focusing on, which is going to be important, is the theory of infrared divergences. So for now, I only talked about UV renormalization. You can also do the renormalization for the IR divergences, which typically would be discussed in terms of the SCAD, soft collinear effective theory. So there's actually some toy models before doing this in the full-blown QCD. You can actually do it in a cubic theory in 6 dimensions or in N-Cus for superior mills, which have a simpler infrared structure. Okay, so for that, you would have to modify the ansatz that you work with because of the different nature of soft and collinear divergences. You can also talk about the operator mixing. You can talk about effective field theory, try to make connections with positivity bounds that nowadays people put on Wilson coefficients. And likewise, I have this dream that maybe we could understand a similar structure using path integral, kind of a la Podzinski. Though I would welcome any suggestions of how to do it. It's more of a vague idea. Okay, so before wrapping up, let me once again highlight the work of great students, Amaya, Dan, and John. So actually, Dan and John are currently on the postdoc market if you're interested in these kind of topics. So with that, let me thank you for your attention and ask for any questions.
Any questions for Sebastian?
I have kind of an open-ended question. Can you just go back to your conclusion slide, maybe? So, can you say something that you learned or hope to learn, big picture, about the renormalization group from this method? So far, I mean, I understood what you did, but it was mostly sort of rederiving known things in a different way. And I just wonder, kind of, what's your ambition?
Yeah, I think the first ambition. So I think the most important thing to me is the kind of computational efficiency. So here it's a little bit hidden. Like we've seen a lot of efficiency, for example, in here. Like you get a much simpler recursion relation, so you have to work much less to compute the cuts rather than computing the RG. Okay, so that's one. The hope is that a similar thing would continue to hold to higher orders, and this would actually allow us to constrain, say, beta functions to higher loops. So like as a kind of a computational tool. But at the same time, so there's certainly that motivation, and it's always good to have that. At the same time, I think that there's something deeper there that should be understood about why exactly unitarity is so constraining that it implies running, at least through these orders. And I think that that's something that should be studied from different perspectives as well.
Yes.
Do you have intuition for whether something similar could play out in a non-renormalizable period?
Yeah, so the question is essentially, I guess, about the irrelevant couplings. So yeah, that's something that we're also thinking about. In principle, you can extend the ansatz of the type that I showed you before. Even at low loop orders, what you can do is you can add irrelevant terms, so things that decay with the constant, with the scale rather. And I think it's clear that you're going to get constraints on those. And in a sense, this is the thing that I mentioned on the last slide in here, that in a sense we already know about certain positivity bounds that are implied by unitarity. So in those cases, people use partial wave unitarity, and only the lower bound on the, say, the imaginary part being positive as the constraint. So to me, it's clear that we have to get stronger bounds if we use full-blown unitarity. But how to do it in practice is an open question. I don't know.
Any further questions? Okay, if not, let's thank Sebastian again.
Thank you.
Thank you.